Soil mechanics is a branch of engineering mechanics that describes the behavior of soils. It differs from fluid mechanics and solid mechanics in the sense that soils consist of a heterogeneous mixture of fluids and particles, but soil may also contain organic solids, liquids, and gases and other matter. Along with rock mechanics, soil mechanics provides the theoretical basis for analysis in geotechnical engineering, a subdiscipline of civil engineering, and engineering geology, a subdiscipline of geology. Soil mechanics is used to analyze the deformations of and flow of fluids within natural and man-made structures that is supported on or made of soil, or structures that are buried in soils. Example applications are building and bridge foundations, retaining walls, dams, and buried pipeline systems. Principles of soil mechanics are also used in related disciplines such as engineering geology, geophysical engineering, coastal engineering, agricultural engineering, hydrology and soil physics. This article describes the genesis and composition of soil, the distinction between pore water pressure and intergranular effective stress, capillary action of fluids in the pore spaces, soil classification, seepage and permeability, time-dependent change of volume due to squeezing water out of tiny pore spaces, also known as consolidation, shear strength and stiffness of soils. The shear strength of soils is primarily derived from friction between the particles and interlocking, which are very sensitive to the effective stress. The article concludes with some examples of applications of the principles of soil mechanics such as slope stability, lateral earth pressure on retaining walls, and bearing capacity of foundations. Genesis and composition of soils. Genesis. The primary mechanism of soil creation is the weathering of rock. All rock types may be broken down into small particles to create soil. Weathering mechanisms are physical weathering, chemical weathering, and biological weathering. Human activities such as excavation, blasting, and waste disposal may also create soil. Over geologic time, deeply buried soils may be altered by pressure and temperature to become metamorphic or sedimentary rock, and if melted and solidified again, they would complete the geologic cycle by becoming igneous rock. Physical weathering includes temperature effects, freeze and thaw of water in cracks, rain, wind, impact and other mechanisms. Chemical weathering includes dissolution of matter composing a rock and precipitation in the form of another mineral. Clay minerals, for example, can be formed by weathering of feldspar, which is the most common mineral present in igneous rock. The most common mineral constituent of silt and sand is quartz, also called silica, which has the chemical name silicon dioxide. The reason that feldspar is most common in rocks but silicon is more prevalent in soils is that feldspar is much more soluble than silica. Silt, sand, and gravel are basically little pieces of broken rocks. According to the Unified Soil Classification System, silt particle sizes are in the range of 0.002 mm to 0.075 mm and sand particles have sizes in the range of 0.075 mm to 4.75 mm. Gravel particles are broken pieces of rock in the size range 4.75 mm to 100 mm. Particles larger than gravel are called cobbles and boulders. Transport. Soil deposits are affected by the mechanism of transport and deposition to their location. Soils that are not transported are called residual soils. They exist at the same location as the rock from which they were generated. Decomposed granite is a common example of a residual soil. The common mechanisms of transport are the actions of gravity, ice, water, and wind. Wind-blown soils include dunes, sands, and loess. Water carries particles of different size depending on the speed of the water, thus soils transported by water are graded according to their size. Silt and clay may settle out in a lake, and gravel and sand collect at the bottom of a riverbed. Wind-blown soil deposits also tend to be sorted according to their grain size. Erosion at the base of glaciers is powerful enough to pick up large rocks and boulders as well as soil. Soils dropped by melting ice can be a well-graded mixture of widely varying particle sizes. Gravity on its own may also carry particles down from the top of a mountain to make a pile of soil and boulders at the base. Soil deposits transported by gravity are called colluvium. The mechanism of transport also has a major effect on the particle shape. For example, low-velocity grinding in a riverbed will produce rounded particles. Freshly fractured colluvium particles often have a very angular shape. Soil composition. Soil mineralogy. Silts, sands and gravels are classified by their size, and hence they may consist of a variety of minerals. Owing to the stability of quartz compared to other rock minerals, quartz is the most common constituent of sand and silt. Mica and feldspar are other common minerals present in sands and silts. The mineral constituents of gravel may be more similar to that of the parent rock. The common clay minerals are montmorillonite or smectite, alita, and kaolinite or kaolin. These minerals tend to form in sheet or plate-like structures, with length typically ranging between 10-7 meters and 4 by 10-6 meters and thickness typically ranging between 10-9 meters and 2 by 10-6 meters. And they have a relatively large specific surface area. The specific surface area is defined as the ratio of the surface area of particles to the mass of the particles. Clay minerals typically have specific surface areas in the range of 10 to 1,000 square meters per gram of solid. Due to the large surface area available for chemical, electrostatic, and van der Waals interaction, the mechanical behavior of clay minerals is very sensitive to the amount of pore fluid available and the type and amount of dissolved ions in the pore fluid. To anticipate the effect of clay on the way a soil will behave, it is necessary to know the kinds of clays as well as the amount present. As home builders and highway engineers know all too well, soils containing certain high-activity clays make very unstable material on which to build because they swell when wet and shrink when dry. This shrink and swell action can easily crack foundations and cause retaining walls to collapse. These clays also become extremely sticky and difficult to work with when they are wet. In contrast, low-activity clays, formed under different conditions, can be very stable and easy to work with. The minerals of soils are predominantly formed by atoms of oxygen, silicon, hydrogen, and aluminum, organized in various crystalline forms. These elements, along with calcium, sodium, potassium, magnesium, and carbon, constitute over 99% of the solid mass of soils. Grain size distribution. Soils consist of a mixture of particles of different size, shape and mineralogy. Because the size of the particles obviously has a significant effect on the soil behavior, the grain size and grain size distribution are used to classify soils. The grain size distribution describes the relative proportions of particles of various sizes. The grain size is often visualized in a cumulative distribution graph which, for example, plots the percentage of particles finer than a given size as a function of size. The median grain size is the size for which 50% of the particle mass consists of finer particles. Soil behavior, especially the hydraulic conductivity, tends to be dominated by the smaller particles. Hence, the term effective size, denoted by, is defined as the size for which 10% of the particle mass consists of finer particles. Sands and gravels that possess a wide range of particle sizes with a smooth distribution of particle sizes are called well-graded soils. If the soil particles in a sample are predominantly in a relatively narrow range of sizes, the sample is uniformly graded. If a soil sample has distinct gaps in the gradation curve, e.g., a mixture of gravel and fine sand, with no coarse sand, the sample may be gap-graded. Uniformly graded and gap-graded soils are both considered to be poorly graded. There are many methods for measuring particle size distribution. The two traditional methods are sieve analysis and hydrometer analysis. Sieve analysis. The size distribution of gravel and sand particles are typically measured using sieve analysis. The formal procedure is described in ASTM D691304. A stack of sieves with accurately dimensioned holes between a mesh of wires is used to separate the particles into size bins. A known volume of dried soil, with clods broken down to individual particles, is put into the top of a stack of sieves arranged from coarse to fine. The stack of sieves is shaken for a standard period of time so that the particles are sorted into size bins. This method works reasonably well for particles in the sand and gravel size range. Fine particles tend to stick to each other, and hence the sieving process is not an effective method. If there are a lot of fines present in the soil, it may be necessary to run water through the sieves to wash the coarse particles and clods through. A variety of sieve sizes are available. The boundary between sand and silt is arbitrary. According to the Unified Soil Classification System, a number 4 sieve having 4.75 mm opening size separates sand from gravel, and a number 200 sieve with an 0.075 mm opening separates sand from silt and clay. According to the British standard, 0.063 mm is the boundary between sand and silt, and 2 mm is the boundary between sand and gravel. Hydrometer analysis. The classification of fine-grained soils, i.e., soils that are finer than sand, is determined primarily by their Atterberg limits, not by their grain size. If it is important to determine the grain size distribution of fine-grained soils, the hydrometer test may be performed. In the hydrometer tests, the soil particles are mixed with water and shaken to produce a dilute suspension in a glass cylinder, and then the cylinder is left to sit. A hydrometer is used to measure the density of the suspension as a function of time. Clay particles may take several hours to settle past the depth of measurement of the hydrometer. Sand particles may take less than a second. Stoke's law provides the theoretical basis to calculate the relationship between sedimentation velocity and particle size. ASTM provides the detailed procedures for performing the hydrometer test. Clay particles can be sufficiently small that they never settle because they are kept in suspension by Brownian motion, in which case they may be classified as colloids. Mass-volume relations. There are a variety of parameters used to describe the relative proportions of air, water and solid in a soil. This section defines these parameters and some of their interrelationships. The basic notation is as follows: and represent the volumes of air, water and solids in a soil mixture, and represent the weights of air, water and solids in a soil mixture, and represent the masses of air, water and solids in a soil mixture, and represent the densities of the constituents in a soil mixture. Note that the weights, W, can be obtained by multiplying the mass, m, by the acceleration due to gravity, g, e.g. specific gravity is the ratio of the density of one material compared to the density of pure water of a material by the acceleration due to gravity. Density, bulk density, or wet density, are different names for the density of the mixture, i.e., the total mass of air, water, solids divided by the total volume of air, water and solids. Dry density is the mass of solids divided by the total volume of air, water and solids. Buoyant density, defined as the density of the mixture minus the density of water, is useful if the soil is submerged under water, whereas the density of water content is the ratio of mass of water to mass of solid. It is easily measured by weighing a sample of the soil, drying it out in an oven and re-weighing. Standard procedures are described by ASTM. Void ratio is the ratio of the volume of voids to the volume of solids. Porosity is the ratio of volume of voids to the total volume, and is related to the void ratio. Degree of saturation is the ratio of the volume of water to the volume of voids. From the above definitions, some useful relationships can be derived by use of basic algebra. Effective stress and capillarity. Hydrostatic conditions. To understand the mechanics of soils, it is necessary to understand how normal stresses and shear stresses are shared by the different phases. Neither gas nor liquid provide significant resistance to shear stress. The shear resistance of soil is provided by friction and interlocking of the particles. The friction depends on the intergranular contact stresses between solid particles. The normal stresses, on the other hand, are shared by the fluid and the particles. Although the pore air is relatively compressible, and hence takes little normal stress in most geotechnical problems, liquid water is relatively incompressible, and if the voids are saturated with water, the pore water must be squeezed out in order to pack the particles closer together. The principle of effective stress, introduced by Kulterzagi, states that the effective stress sigma may be calculated by a simple subtraction of the pore pressure from the total stress, where sigma is the total stress and U is the pore pressure. It is not practical to measure sigma directly, so in practice the vertical effective stress is calculated from the pore pressure and vertical total stress. The distinction between the terms pressure and stress is also important. By definition, pressure at a point is equal in all directions, but stresses at a point can be different in different directions. In soil mechanics, compressive stresses and pressures are considered to be positive and tensile stresses are considered to be negative, which is different from the solid mechanics sign convention for stress. Total stress for level ground conditions. The total vertical stress at a point, on average, is the weight of everything above that point per unit area. The vertical stress beneath a uniform surface layer with density and thickness is, for example, whereas the acceleration due to gravity, and is the unit weight of the overlying layer. If there are multiple layers of soil or water above the point of interest, the vertical stress may be calculated by summing the products of the unit weight and thickness of all of the overlying layers. Total stress increases with increasing depth in proportion to the density of the overlying soil. It is not possible to calculate the horizontal total stress in this way. Lateral earth pressures are addressed elsewhere. Pore water pressure. Hydrostatic conditions. If there is no pore water flow occurring in the soil, the pore water pressures will be hydrostatic. The water table is located at the depth where the water pressure is equal to the atmospheric pressure. For hydrostatic conditions, the water pressure increases linearly with depth below the water table, whereas the density of water, and is the depth below the water table. Capillary action. Due to surface tension, water will rise up in a small capillary tube above a free surface of water. Likewise, water will rise up above the water table into the small pore spaces around the soil particles. In fact, the soil may be completely saturated for some distance above the water table. Above the height of capillary saturation, the soil may be wet, but the water content will decrease with elevation. If the water in the capillary zone is not moving, the water pressure obeys the equation of hydrostatic equilibrium, but note that is negative above the water table. Hence, hydrostatic water pressures are negative above the water table. The thickness of the zone of capillary saturation depends on the pore size, but typically, the heights vary between a centimeter or so for coarse sand to tens of meters for a silt or clay. In fact, the pore space of soil is a uniform fractal, e.g., a set of uniformly distributed d-dimensional fractals of average linear size L. For the clay soil, it has been found that L equals 0.15 mm and D equals 2.7. The surface tension of water explains why the water does not drain out of a wet sand castle or a moist ball of clay. Negative water pressures make the water stick to the particles and pull the particles to each other. Friction at the particle contacts make a sand castle stable, but as soon as a wet sand castle is submerged below a free water surface, the negative pressures are lost and the castle collapses. Considering the effective stress equation, if the water pressure is negative, the effective stress may be positive, even on a free surface. The negative pore pressure pulls the particles together and causes compressive particle-to-particle contact forces. Negative pore pressures in clayey soil can be much more powerful than those in sand. Negative pore pressures explain why clay soils shrink when they dry and swell as they are wetted. The swelling and shrinkage can cause major distress, especially to light structures and roads. Later sections of this article address the pore water pressures for seepage and consolidation problems.